Well, thanks for having me today. I'm Pete Kirkpatrick. I'm a principal engineer and a hardware architect at Pure Storage. And it was great to have Ray kind of cover a lot of different technologies. I'm going to focus on one or a few of those in particular, which is really NVMe and NVMe over Fabrics. And we can talk a little bit about the basics, some of our experience with it, and then hopefully, what's the potential of this technology, because I think there's some exciting things we can do. So I wanted to start by kind of, remembering back a little bit and then looking forward. It's about 10 years now when NAND became cheaper than DRAM on a price per bit basis. And, at that time, there was a lot of excitement that we could get these, 10 gigabyte SSDs and put them in our PCs and everything could go faster. And there was a lot of excitement then, but, the price was still prohibitive and it took us a long time to get to where we are now, which is we can put a petabyte of that NAND flash in a really tiny package and get a huge amount of performance and benefit out of it. So things really have changed quickly since that. Economics really drive a lot of those factors. And now that few gigabyte SSD is now, we're seeing things like 60 terabyte SSDs coming out. And I think this is probably still a little bit in the future. People have been able to show this, but it's not really a mainstream thing. But the density and Moore's law keeps happening there, and so that's just another benefit of Moore's law and having that technology and density just increasing over time. And the new technologies that Ray introduced for both NVMe and NVMe over Fabrics are really playing a big role in how we can start to utilize technology like this, because the fact is, when we put that much potential and that much flash behind kind of a traditional interface that was built for spinning disk, we're really starting to hinder the performance and the potential that we can get out of that device. And then something I won't talk too much more about, but Ray also covered well, was 3D NAND, TLC NAND. That stuff's not even new anymore. That is a mainstream technology, but we're not going to stop there. We're going to keep going in higher densities, higher performance. QLC will come along one of these days and be a viable media. The 3D XPoint is very exciting, and there's, I would say that NVMe isn't just going to enhance the use of 3D XPoint. It's going to be required if you want to use 3D XPoint outside your memory bus. So this is just kind of to set up the fact that, things have always been changing quickly. It probably seems to everyone in the room that they're changing even more quickly every day. And with all these things happening, you have to be able to have an architecture, a system architecture or an IT infrastructure that can accommodate these new technologies as they show up and try to take full advantage of them. So I wanted to start a little bit by diving into NVMe and just the kind of a little bit of the theory of operation, and then we'll bring it back up and kind of see, what does this do for us? And so really anybody that's familiar with the technology or even read the spec, they'd say, well, you kind of stole this from page 1 of the spec, and it's true. But this is really great because you can look at kind of one diagram and get really the main point of the technology and how it works. So really, just simply what it really is a high throughput, high performance, low latency protocol that's really designed to take advantage of the modern CPUs and flash. It's really designed to work natively on PCI Express, and that in itself is one aspect of high performance, because if you get a 2-socket Intel server these days, you've got about close to 80 gigabytes of PCI Express coming right off the main CPU complex. So directly attaching this kind of storage gives you a huge amount of performance. The cool thing about it is, and Ray touched on this, you can also go and transport that protocol out over many fabrics. I kind of chose to highlight RDMA and Ethernet. I think that's kind of the one with the biggest potential, especially for new and modern deployments. But if you've got an InfiniBand fabric, or if you've got a fiber channel fabric, you can kind of use those in place and then run the new technology over the top. So to get down to, why is this going to provide us performance? Like really what's changing that gets us there? And it's really this structure of queues. And typically a queue that's created is created in a pair. So we call that a submission queue and a completion queue. And any core, any hyperthread, even on a CPU, can get one of these queue pairs, and it can actually get one for every SSD that's in that domain, that's in that system. And so, if you look at it here, this is kind of a multi-core, 2-core CPU in this case, and CPUs are getting to. You can get a 28-core CPU from Intel. It's actually got 56 hyperthreads. You put that in 2 sockets, and you're up over 100 CPUs. You put that in a system with 100 SSDs, and you've literally got a path between every one of those threads and every SSD. So a process that's running here can put work on the submission queue. Maybe it's just do this read. You submit that command, and you ring the doorbell on the device for this queue, and the device does all the work. It does, it fetches the command, it does the RDMA, or DMA in this case, to move the data. And once the data is put back in main memory, it just gives you a little bit of an interrupt, and the process can continue on, doing its actual job. So the overhead of submitting that work and completing the work and communicating with the storage is drastically reduced. And so that's really fundamentally why we get higher performance and better latency out of this kind of system. Another couple points here is when every core has access to every SSD independently, there's no more locking between the processes on trying to access storage. If you need to get a bit of data, you go and do it. There's no waiting on other processes, and that in itself gives you a lot more efficiency, eliminates a lot of overhead in the system. And I want to take just a moment to kind of give a shout out to the folks that actually developed this standard, because I think this kind of technology can live or die on the quality of the standard, the cleanness of how it's written and presented. And this one is particularly well done. So a lot of folks have contributed to that and kind of brought us to where we are. Okay, so these are some really simple pictures. But I wanted to kind of compare and contrast with what I thought about putting yesterday and today on these. But today traditionally SCSI is what still is kind of the mainstream technology that folks are using. So if this is just a server with a lot of CPU cores, or if it's a storage system where it's got a lot of SAS SSDs in it, the way these are typically connected is through a SAS HBA. If this becomes a bigger topology, you've got SAS expanders and so forth, but I wanted to keep it nice and simple. So, for a process running on one of these cores to get to storage, it's typically got to go context switch into the kernel. You've got to access, probably several layers of the SCSI stack to do all the different functions that we expect before getting down to the SAS driver, where I've got to take a lock on the port. And from the SAS device, I've got to then, arbitrate a path all the way through a bunch of expanders down to my SSD target. And once all that's done, I can start to transfer data. And so I maintain that connection until the data is transferred. At the end of the day, I get the work done. And meanwhile, all my neighbors are kind of waiting for their turn to access storage. And so that's really highlighting how inefficient things have become. And that's what happens, technology builds up solutions to problems over time, and then after a while, there's a lot of cruft in there. So with NVMe, again, what we're going to do is a process on this core wants to do some I/O, it just does I/O. So it will, submit work into its submission queue. The SSD that's going to have that data will start to do the work, return the data or write down the data, put the completion on the completion queue, and then we're done. Today that's probably typically done through a kernel driver still, but you're avoiding a lot of the SCSI stack, and then from the driver down to the SSD, it's very efficient. And now one cool thing is folks are starting to play more and more with user mode drivers. And so you can literally go from an application to the SSD without even going through your kernel. So that kernel bypass is another aspect of how we can get more and more performance. So my next picture is going to look almost the same, but this is really the parallel thinking about how would you go and deploy NVMe over Fabrics. And it's the same thing. So here we kind of have two little servers. Again, they're going to have a SCSI stack. They're going to use a Fiber Channel HBA as initiator, go through the SAN itself to get down to storage arrays or SAN arrays that are, again, going to have a SCSI stack and so forth. And so we're going to have all of that overhead twice. We're going to have it on the client side. We're also going to have it on the server and the storage side. And then just like before, now if you have different servers and each of those have NVMe over Fabrics technology, they can have multiple queues over the fabric to all of the different storage arrays. And I didn't bother drawing all the lines because all you would see is just lines. The parallelism is so massive that it's you actually have to simplify even just to draw kind of a really small system like this. And then one thing I should probably point out is what I'm trying to get to here is kind of the logical path that you're going to connect everything. So of course, if you're going to go out over a fabric, you're still going to have RDMA NICs. The fabric itself is going to be an Ethernet. And so physically, these systems are going to look almost exactly the same. And in fact, there is a way to enable NVMe over Fabrics on Fiber Channel. So the hardware is really going to look the same, but it's really this logical method of accessing things in this high parallelism that's really giving us the advantage. Okay, so I've decided this is really exciting and I love technology, so, what am I going to get? What am I going to get out of this? And of course, what we've kind of been through a lot is you're going to get higher throughput and you're going to get lower latency. That's always great. Systems become more efficient. One of the really exciting things for me as a system designer is that I get much lower utilization of the CPUs on my system. And you can translate that into a couple different directions. You could say, well, now I'm using fewer CPU cores to do the I/O kind of work, but I still have all those CPU cores, and so I'm going to do more work. So, you can start to multiply the capability of a system just by utilizing the CPUs better. Or you might say, I'm actually happy with the performance of my system, and I'm going to put, fewer CPU cores in there, and they can be fairly expensive. And so if you can save dollars, save power, and of course that translates into cooling, you can get just a better cost, for your hardware and even for your whole environment. So that kind of flexibility that comes from efficiency is really powerful. You can start to control more your performance versus your cost profile. And then, I touched on this before, is when SSDs are starting to get so big in the multi-tens of terabytes kind of range, we don't want to have all that potential horsepower hidden behind a little drinking straw. So increasing the width of the interface and accessing over this parallel methodology is really enabling SSDs to continue to grow and not get strand all that capacity. I think the risk we have there if we don't evolve in this direction is that we'll end up just like we did with the end of the spinning disk era, where you have a server with racks and racks and racks of disks behind it, where every one of them is short stroked, and you really end up wasting a lot of capacity just to get the performance you need. I met a gentleman the other day who he short-stroked his hard drive so well that he figured out that he was on exactly one track and it never did any seeks. And I thought, well, yeah, you can always take something to the extreme, but in this case, we're going to be able to make these huge SSDs and access all the performance. Okay, so again, we all love shiny new technology, and a lot of these things can create a lot of excitement, especially when they're performance related. But Often that can mean it's expensive or inaccessible if it's not a mature and mainstream technology. And in this case, I think it's pretty clear to folks now that it is going to take over. And our team did some analysis of you know, a lot of different market segments, and you know what you see is that today, where are we? Somewhere in here, most of the world still runs on SATA. But that's because there's a lot of legacy, call it legacy slots for SATA, and you know, there's a lot of momentum in the industry. But we're already seeing that the end of the SATA era or the growth of SATA is kind of upon us already. And meanwhile, what's taking over is NVMe. So if you talk to your SSD vendors and you really start to go into the roadmap with these guys, they'll start to tell you that, you know, we're not going to build any more SATA controllers. We're not going to put our development effort into a technology that's kind of starting to reach its peak and start to decline. Everybody's putting their effort into NVMe controllers, and that's really helped driving a lot of momentum into the mainstream. And then, of course, SAS drives are still around. You know, they're really the bread and butter of kind of a classic enterprise array. And they'll probably still continue to fill a lot of these legacy arrays. But we're also seeing this peak. It's probably hard to see down here. This is all squashed. But the peak for SAS is also happening around the right edge of this chart. And really what's happening is NVMe is going to start to cover both of those segments. And so, you know, the thing you get from SAS is typically it's dual ported. It might be just, you know, other aspects of it give you higher performance, high resiliency. So NVMe can go there and cover that segment. For SATA, it's usually cheaper. It's, you know, I think probably half the people in this room with a laptop do have an NVMe M.2 form factor, kind of gumstick form factor inside. And so you can cover the entire market with this technology. You just optimize for the different segments. And so you've got, you know, users of this technology everywhere from Apple and every one of your mobile devices, your tablets, your laptops, up through the cloud. And a lot of this growth is driven by the cloud vendors. So all of a sudden we all have a lot of things in common, and that will really drive innovation, and it will really drive costs down. Because we all know with semiconductors, wherever the volume is, that's really where the best cost point's going to be. So all of this is really exciting. What I love about our system, we put a little picture in here, is, you know, we designed it this generation starting somewhere over here. And at that time, this trend was not obvious. But we designed it to just handle all three of these devices. We said, you know, you don't have to pick which one. We're going to continuously look at which one can give you the best price, the best performance, the best resiliency. And, you know, no matter what the shape of this chart was in the future, we'd be able to handle it. I was hoping this would be the case, because this is kind of my particular favorite. And I'm really happy that it looks like it's going this direction now. So this is what we did. This is our product we call the Flash Array M. And I want to go into some of the aspects that, you know, why was it ready to take NVMe, and then how did we use it to kind of solve some particular problems in this design. So fundamentally, you know, we talked about the parallelism that you can get between CPUs and storage. If your software is not designed with that methodology in mind from the beginning, you're not going to get anywhere with it. And our Purity software really was designed to be multi-threaded, massively parallel. Every data structure, every processing path is designed for parallelism. And every time we find something that could be a potential limitation, we can go and change the parallelism to kind of accommodate for that. We look across the whole pool of flash that's in the system, and, you know, of course we can attach shelves today, SAS shelves. But we can look over all that flash and kind of manage it all in a big pool. And that gives us a lot of efficiency on how we manage garbage collection, how we treat different drives for resiliency, how we do erasure coding and things like that. And of course, we can treat a pool of SSDs or a pool of flash and get a lot more performance than you can if you're talking to individual SSDs. It's really night and day if you treat them correctly, what you can get out of them. Okay, so how do we use NVMe? It was clear that from the system level, there was going to be different bottlenecks that arise over time as we try to increase performance. And everybody that's worked on a system, it's probably everybody in this room, knows that once you knock one of those bottlenecks down, you're just going to kind of run into the next one. Hopefully you get a little runway out of it. You'll hit into the next one. The first one for us was the write commit buffer into the system. So we call this the NVRAM. I guess most people call it an NVRAM. But if you do a write to the system, what you want really is the fastest acknowledgement that write is committed to durable storage. And so we wanted the lowest latency device, and really all the write throughput of the system has to go through there. So it needs to be both high throughput and low latency. So what's NVMe for? This was kind of the poster child for what you should do with it. So at the time that we did this device, we started shipping in 2015. It was the world's first dual-ported hot pluggable device. And both of those pose some challenges that I'll go into a little bit later. But there's a lot of hardening, and I think Ray kind of went into this, that you've got to have access to your BIOS and to all these different aspects of the system, from the electrical interfaces, the CPU and BIOS, the kernel, the application. Everything needs to be aware of what's happening, both in the resiliency aspect and also to take advantage of the performance. So these devices you can see 4 of them across here. We'll put 2 or 4 in a system. We've got many thousands of these out in the field. So every one of our system runs on these. And my favorite part is, with that new technology out there and the risks that are often perceived with PCI Express, with hot plug, or any new technology, is that we measure the uptime of our entire fleet. Every one of them phones home every 30 seconds, and so we can monitor who's up and who's not. So we measure an availability of 6 nines across our fleet. Now, measuring it is really a good way to show what's actually real versus a calculated. It's easy to calculate 6 nines. The other thing we do is we include. We don't have maintenance windows. When we do an upgrade, we do upgrades. It's very common for our customers to do upgrades during production because there's no loss of performance and there's very little risk of having an outage. And so we include all of time in our metrics, and so we don't say, oh, there was a scheduled downtime, so that doesn't matter. I think that's the most important thing to cover in your availability metrics. So we've really been able to integrate the new technology and maintain this very high, or actually increase our standard of availability. So the next wave is, today we do ship these slots that are connected, SSDs that are connected via SAS. But again, seeing this wave coming and seeing the momentum behind the NVMe SSDs, those slots are all wired for NVMe. And so once that makes sense for our customers and for us, we're gonna be able to populate those, and we'll do all of these transitions non-disruptively, just like we do software upgrades. Okay, so these are probably things we've already touched on all the way throughout, but we'll just kind of, if you're thinking about implementing a system, whether it's within a storage system, whether it's just in a server, whether it's across your entire environment, both for NVMe and NVMe over fabrics, you can ask yourself, is the system performing as well as it can today? Maybe the answer is, yeah, there's all this potential in my CPU and my SSDs, but the software or the interface is in the way. And so is there a critical bottleneck that NVMe could solve and kind of increase my performance? So for us, that was really obvious. Our NVRAM was this high performance, high resiliency device, and changing that really changed the game. We had one customer who upgraded from our old system to our new system. It was all done online, of course, and non-disruptively. And the benefit that he saw from the new NVRAMs, what he could literally double the load. This was a VM case. He could put double the number of virtual machines against the new storage, even though it had roughly the same CPUs and roughly the same kind of capacity. And that was really powerful for them. So that, effectively is reducing their cost and increasing their efficiency. So, how can we use this? How can we integrate the technology in a way that you can have a non-disruptive transition between all the different interfaces that exist? Again, SAS, SATA, NVMe. You do want to be able to handle all of those, and you want to be able to transition between them without disruption. And this one is like, and then eventually we're going to want to mix those types of things. And that's probably one of the best ways to transition, is to say, you've got media in the system, it's got kind of a legacy interface. Let's put media on the new interface, and let's mix those within the system. And over time, the old ones can go away. Do I control the electrical design of my system, the physical design of my system, my BIOS, my motherboards, my kernel, and all the way up to the software? You really have to look through the whole stack to figure out how I can make it resilient and how I can make it really perform well. And then the thing that they wouldn't let me talk about, but is most exciting for me, is once you get this in place, what happens next? It's like, okay, well, now we see this performance benefit. We can kind of see the things that are going to become problems next. And, what do we do? What can we do beyond just working through these bottlenecks? But can we enable an architecture that's really, revolutionary? I'll leave it at that, because that's the stuff that's coming maybe for a talk next year. So are there any questions? Do we have a little bit of time left for questions?
So let's talk NVMe over Fabric. This is the NVMe SSD implementation. So you're talking about implementing the SSDs here in the next gen system.
Well, I'm not talking about our next gen. I'm talking about what we're capable of.
Oh, okay. Okay.
That's where I have to be careful. But again, on the SSDs, we're ready. We can integrate those when the price and performance is right. And on our controllers, we have modular I/O. So internal, if it's in, these controllers plug in the back, so you can't see them. The internal interfaces are ready for NVMe, and the external interfaces are just NICs and HBAs, and so we're ready to implement NVMe over Fabrics as soon as our customers are.
Interesting. And so the current technology that you have in these NVRAM devices is like Everspin, or?
It's not. It's DRAM.
It's DRAM battery backed, or
it's classic DRAM, supercap, and flash.
Yeah, I got you.
We don't like battery backed, but
I understand.
Draining the DRAM to flash is well understood. It works great. So
yep.
We always consider, and it's fun to consider what goes in there next. Is it MRAM, Crosspoint? I think it'll be DRAM, supercaps, and flash for a while.
All right, thanks.
Any other question? Good.
All right.
So the FlashBlade is also able to do this sort of thing as well? Is that so? You guys are relatively ready to go with NVMe, pretty much.
Yeah, FlashBlade is.
First, you might tell them what FlashBlade is.
Yeah, sorry. Thank you for introducing that. So this is kind of our first product line, Flash Array. FlashBlade is designed to be a scale out, focused on NFS and file storage, and we get the best of both worlds across the two product lines. We get a really nice high performance kind of classic enterprise array, and then we have a scale out platform. Everything is interconnected with Ethernet. I'd say the principle of operation is all very similar to what we're talking about here. but I can't go too much into the detail on what's inside the guts. Maybe that'll be another talk for another day too.
There's been some discussion that although NVMe has been hot pluggable for a while, there's been some challenges at the system level to support that sort of thing. You guys have any of that?
We had the challenges for sure. I would say the perception that it's extremely difficult in the past came from, if you want to support a system where any type of device is pluggable on top of any kind of operating system, that's a hard problem to solve.
Yeah.
But when you control everything and you control the OS, you control the application, you control the devices, they become solvable. But there are a lot of gotchas. You just got to grind through everything, and you've got to obsessively test the product. You've got to test a lot of the product. You got to monitor in the field, and you've got to be able to react to anything that happens. But if you're careful and you pay attention to it, you can kind of grind through all the issues.
Okay, thanks.
Any other question?
Okay, thank you.
Thank you very much.